Well, Ohm's law. Let's change the color of our pen. So, Ohm's law says, take the current, multiply by the resistance. So this voltage here will be R1 I out. It's very important to remember that this is the voltage value and the sign of the voltage is positive here, negative here. Why? Because the current is going this way, not this way. Okay, very good. So let's see now what we can do. What I could do is I could try to write a KVL around this loop. Or let's see if there's a quicker way of doing that. Okay, so if I have this I out, if the current through L1 is called I out, do we know the voltage on L1? Well, L1 says, if you give me the current with its derivative, I can give you the voltage. So what we know is that the voltage across L1 is equal to L1 times dI1. That's the current flowing through the inductor from top to bottom, which we called I out. So dI out over dt. That's the voltage across L1. Okay, so now we found the voltage across R1, this amount with this polarity. We found the voltage across L1, this amount with what polarity? This polarity, right? Why? Because we always have to go back to that fundamental equation. That fundamental equation said if the current is flowing inward to the top terminal, if the voltage measured as positive here, negative here, then we have this relationship, right? So I'm applying that relationship here. So now we are ready to write a KVL. We start from anywhere we want. Let's say start from here. We're going from positive to negative. So I'm going to write positive this value. So plus R1 I out. Then I'm going this way. I reach positive. So I'm going to find this voltage expression and I will write positive. Plus L1 dI out over dt. And because I'm going back to the same point, this will be 0. This is a differential equation governing the behavior of the circuit. And we know one more thing, and that's that I out is equal to, at time equals 0, is equal to I0. Right? We said that when we start the circuit and we take a snapshot of the current through this guy, it carries an amount of I0, let's say 1 milliamp. Okay, so now we need to solve this differential equation subject to this initial condition. Right? That's pretty simple. So again, we move things around. We take this guy to the other side, divide by L1, cross multiply, so we'll have di out over I out, dt over minus R1 L1, and we write our logs and all that. So it's pretty simple, right? So what we will see is the following. Okay, so let me just make sure that there's one little difference with respect to the RC circuit. I have to be careful here. So let me take this to the other side, and I'm going to write it like this. So we have I out is equal to minus L1 over R1 dI out over dt. So in the case of the RC circuit, we saw that the time constant was equal to the resistance multiplied by the capacitance. In this case, what we see is that we have a ratio of L and R, right? Not the product of L and R. So once we solve this, we end up with the following. So I out of t will be given by, it's an exponential that decays, so it will have a value of I0, then exponential of minus t. Now, there's a time constant here, right? And that time constant is given by L1 over R1. Okay, so that's the difference between the time constant of this RL circuit and time constant of the RC circuit we saw before. So L1 over R1 is called the time constant. Okay, so that's good to know. Let me make sure that I have some good examples to look at. All right, now in both cases, the RC circuit and the RL circuit, we saw that we had a T here and then we had a time constant here. Time constant obviously has to have the unit of time, the dimension of time, right? Now, is that a coincidence? Why should it be that this is time and this should also be time? Well, it has to be, because you cannot take the exponential of a quantity that has a dimension. The exponential of a quantity is only meaningful if this quantity has no dimension, no unit. So whatever unit we have here, you have to have on the bottom as well, so that they cancel each other. This quantity becomes dimensionless, then we can take the exponential. And that's why we ended up like that. Okay, all right, so let's plot this as a function of time. Nothing dramatic here, really. So we have I out, which is the current flowing through this loop here, as a function of time. At time 0, what did we expect? I0, right? So it starts at I0. As you can see, when t equals 0, that's 1, you get I0. And as time goes by, this current just decays. So it goes down exponentially towards 0. And the time constant is L1 over R1. All right, so this is strange. This says that the time constant depends on L1, so the larger the inductance, the longer the time constant, but it's inversely proportional to the resistance. So the larger the resistance, the shorter the time constant. That's in contrast to what we saw for RC circuits, where the larger the resistance, the larger the time constant. So you have to be careful about these two and make sure you don't confuse them. Okay, so that's an example of a simple RL circuit that consists of just a resistor and an inductor, nothing else in the world. And all we did is we gave an initial current to the inductor so that the circuit actually does something interesting, right? Otherwise, there wouldn't be anything. All right, so that's one interesting example. Let me give you another example to see how that comes about. We'll try to solve this one in the time that we have. So here's another example of an RL circuit. Okay, so here's what we have. We have a resistor and an inductor, L1, R1, and V, V1. And again, we want to solve the circuit. And what we're assuming is that at time 0, just before we look at the circuit and the circuit starts doing something interesting, let's assume that there's a current through this inductor. And actually, we know how much that current is. So let's assume that that current is equal to the following. So let me put it this way. Let's suppose that we connected the circuit like this. And, okay, well, maybe I'll do this to make it more interesting. Okay, so let's say I0 is equal to 0. Remember, we did the same thing with the RC circuit. When there was a battery here, we assumed the voltage on the capacitor was 0, the initial condition. So here we also assume the initial condition on the inductor is 0. Okay, now we start and see what happens. All right, well, again, we look at it qualitatively just to get comfortable with the circuit before we write equations. There's a voltage source here. So there's some amount of voltage here. There's no current to the inductor. Okay. All right. If there's no current through the inductor, there's no current through the resistor. That okay? We have a KCL here, so no current here, no current here. If there's no current through R1, the voltage drop on R1 is 0. So there's no voltage from here to here. Alright, so I will use a different color just to summarize everything that I'm finding as I go along so that I don't get confused. So here's an orange color. So this voltage is 0. Why? Because this current is 0. I equals 0. This is all at the beginning of time. Okay, now why is this current 0? Because this current is 0, right? We assume the current through the inductor was 0. Okay, then how much is this voltage? Do we know at time 0? Just when we start the circuit? Well, if you write the KVL, you write minus V1 plus this voltage, which is 0, plus this voltage, let's call this a voltage V out, plus V out, going back to the same point, equals 0. So that says that V out is equal to V1 at t equals 0. Okay, so this voltage appears here. All right, so when we start out the circuit, there's no current here, and what we observe is that this guy has no current, this guy has no voltage, so all this voltage has to appear here. Okay, that's interesting. So now, what exactly happens? Well, because we have a voltage on this inductor, the inductor wants to draw a current. So the current through the inductor keeps increasing with time. And so what we expect is, again, very qualitatively speaking, if we monitor the current to the inductor, so we're going to call this I out. So in this case, you might say both V out and I out are of interest to us. I out as a function of time. So initially it's 0, because we assume it was 0. And as time goes by, we draw some current through this resistor and inductor. So this current goes up. And where will it go? Well, maybe it reaches a constant value. We don't know, right? So if it does reach a constant value, how much should that be? So let's put a question mark here. Well, let's suppose this current does become constant. If the current becomes constant, then I'm going to write V equals L di over dt. So if the current through the inductor has reached a constant value, its derivative is 0, the voltage on the inductor is 0. So if you wait a long time for this current to reach a constant value, the voltage across the inductor is 0. Okay? So then right around here, the circuit becomes very interesting. So I'm going to draw the circuit right here. Okay? This is the snapshot of the circuit at very, very long time past 0. Okay? Right here. We have a battery, no problem. So we're going to draw the battery with an amount of V1. We have a resistor, no problem. And we have an inductor with a voltage of 0 on it and a constant current through it. So if a two-terminal device guarantees that the voltage across it is 0, what do you call that two-terminal device? We call it a short circuit, right? So the inductor actually acts like a short circuit because the voltage that it sustains is 0. Right? If it wants to keep that voltage to 0, then it will be a short circuit. So at much time past time 0, the circuit reduces to this. So do we know this current? Yes, because we have 0 here, we have V1 here, so the voltage on R1 is V1 minus 0 over R1. So the value of the current that flows through the inductor at time infinity should be equal to, this value here will be equal to V1 over R1. Because at time infinity, this current has stopped changing. This voltage is 0 from this equation. When the voltage is 0, the inductor acts like a short circuit. The inductor acts like a short circuit. The circuit reduces to this. So all we have is V1 minus 0 over R1. That's the current that we get. So qualitatively speaking, that is our guess about the behavior of the circuit as time goes by, the transient response of the circuit. Now, of course, we have to write careful equations and make sure that that's true. Okay, so that shouldn't be that hard, right? In general, what we know is that if this current is called I out, this voltage is called L di out over dt. So V out is equal to L di out over dt at any time, right? At any point in time. Now, if this current is I out, what's the voltage across R1? So voltage across R1 is equal to I out times R1. So I hope you're not confusing. This 0 was only for time 0, okay? So it's no longer valid as time goes by. And similarly this one. So now I have the voltage across R1 is this much. I have the voltage across the inductor is this much. I'm going to write the KVL. So I will write minus V1 plus R1 I out, this guy here. And then I'm going this way, that's V out, and that's L di out over dt. L di out over dt, this has to be 0. So we have a simple differential equation, and with an initial condition of 0. So we just have to solve that differential equation and see what we get. And the result is very simple. So I out as a function of t comes out to be, because the initial value is 0, the final value is V1 over R1. So it's V1 over R1, 1 minus x POV minus t over L1 over R1. Okay, so if we check this result, which just comes from solving this differential equation, things are sensible. At time equals 0, this is 1, 1 minus 1 is 0, I out is 0. We are right here. That's our initial condition. At time equals infinity, this is 0. We get V1 over R1, and that agrees with our calculation before. So that is the behavior of the circuit as a function of time when it starts out with a 0 current through the inductor. If we have I out, we can find everything else. How? If you're interested in this voltage, well, V out is just derivative of I out times L. If you're interested in this current, that's just I out times R1. So that's simple. So all of the quantities in the circuit are now known. So I hope these lectures have been useful, and I wish you the best.